Hello and welcome to the ASCE Southern Arizona Branch virtual tech tour of the El Rio Preserve Bank Protection Project. My name is Deirdre Brosnahan and I'm the project manager for the Pima County Regional Flood Control District on this project. The Pima County Regional Flood Control District is undertaking this project in partnership with the town of Marana to provide low-flow bank protection to the El Rio Preserve. The El Rio Preserve is 104 acres, owned and managed by the town of Marana, where over 200 species of birds have been documented. The El Rio Preserve is located immediately south of the Santa Cruz River in one of the effluent-dominated reaches. In previous years, the Santa Cruz River has broken out and flowed through the El Rio Preserve, reaching what was once a second pond area located east of the existing pond. The continued breaching has made it difficult for Marana to construct improvements and manage the site. Therefore, the intent of the low-flow bank protection is to still allow water from the Santa Cruz River to enter the preserve and maintain floodplain functions, just in a slower and more controlled manner. A notch in the bank protection will allow water to enter and leave the site. This notch is particularly critical in large events where the bank protection overtops, and it needs a path to drain back to the river. Marana has also been provided with an additional low-flow drain pipe for when they need to drain down the site further to do maintenance on the pond. Additionally, the district has also graded an island and terraces for the town to use in developing the site as a premier birding and recreation destination. It takes a large team to design and build soil cement bank protection. On this project, our design team was SOMAS, Solis Engineering provided construction management services, and construction was done by Borderlands. Westland Resources provided our cultural resources monitoring. The district has had many years of experience using soil cement to construct bank protection along our major watercourses here in Pima County. I'd like to introduce our Director and Chief Engineer, Suzanne Shields, to tell you more about the district's history with soil cement.
Hi, I'm Suzanne Shields, the Director of the Regional Flood Control District and the Chief Engineer. And I've been involved with flood control improvements and construction of soil cement since the 1970s. It was originally used, soil cement, as some protection along a few locations along the Santa Cruz River by the Ina Road treatment and Rogers Road treatment plants. And then right after the floods in 1979, it was used along the Rito River and it's a limited application. In 1983, we had the Great Flood of Record, and places that had rock riprap or rock gabions all failed. On the Rito River alone, we lost 150 acres of land. That included people's homes and businesses. What was significant, and this was a flood that was twice the size that was predicted for the Santa Cruz River. What was interesting is the soil cement bank protection held up. It's one of the reasons is because the cement keeps curing and it gets harder and harder. The other thing was that it was thick. You know, most soil cement, when it's laid down on 8-foot wide lifts. So there was a large program to rebuild bridges and channels and bank protection. And we decided to work on using soil cement as our primary form of protection. During that time period, from about 83 to 85, we were working up specifications for soil cement. What were the right mixtures, depending on what the soil conditions. Soil cement is something that's easy for us to construct here as well, because we have a lot of sand, though you do need a certain amount of silt in the mixture. At the same time, we were talking to the U.S. Corps of Engineers. They had just recently completed the Tucson urban study, and with the floods, we were trying to attract federal dollars to help us on the Rito River. To do that, we had to convince them that soil cement was a viable option. We also had to convince them that in our arid Southwest, with our steep streams, that erosion is the real form of flood damage. I worked together with other engineers and wrote the specifications, descriptions of how soil cement could be applied, its uses, its benefits, the reduced cost, ease of construction, and the Corps of Engineers accepted my specifications, and they became the Corps standards. They also accepted that erosion, especially along the Rito where we lost 158 acres, was a real threat to urban development and was something that needed to be mitigated. We were successful in getting a flood control project, the only one, to my knowledge, ever for erosion, approved along the Rito. And so the improvements on the Rito River, both the soil cement bank protection as well as the linear river part, were part of this project that Pima County Flood Control District sponsored with the U.S. Corps of Engineers. And so it provided great benefits, both later when we were having floods in 1993, where we already had soil cement in place, the 2006 flooding on the Rito, which was a 250-year storm. We literally had no damages to private and public infrastructure. That's a real difference from all the bridges that were destroyed or washed out, as well as all the loss of all the homes, businesses, and land. The Rito was one of our first success stories, but we also used it along the Santa Cruz River. Even prior to coming to Pima County in 1976, I helped design the soil cement bank protection to Rio Nuevo. So, soil cement and me, we're a pair. We go together.
Now that you've learned about the district's history with soil cement, let's go through how it's made. This is the soil cement plant. It's here that we make soil cement by combining native material from the stockpile with cement, water, and fly ash. The percent cement is determined by a mix design and confirmed by sampling and breaking soil cement cylinders to demonstrate that they've reached the required strength of 750 psi by 7 days. On this project, our percent cement ranged from 7 to 9%. The stockpile is comprised of native material harvested from the project site, which is sampled to confirm it's within our specifications, after which it can be placed in the stockpile. From there, the native material is loaded into the soil cement plant and screened for cobbles. Those cobbles are rejected and fall into a hole adjacent to the plant that is emptied as it fills. After screening for cobbles, the remaining native material is mixed with cement, water, and fly ash, which are all weighed and controlled by the soil cement plant's computer to get exactly the right ratios. This material is mixed in the hopper before it continues down the belts and gets loaded into the trucks. The plant is powered by a large generator and controlled via a computerized workstation. The plant operator has video feeds throughout the plant to monitor production. The first step in building soil cement bank protection is prior to the plant producing any soil cement. First, the vegetation must be cleared from the footprint of the soil cement prism. From there, the toe trench is excavated to final depth. That depth is dictated by the 100-year scour depth of the adjacent channel. The toe trench side slopes are shaped to a 1-to-1 for the soil cement to rise up along. When the toe trench and the side slopes are ready, then soil cement placement can begin. Soil cement from the plant is hauled by trucks over to the toe trench, where it's deposited in windrows. A monitor standing along the top of the bank tells each driver when it is time to begin emptying their truck, so that the uniform ribbon of soil cement goes between ramp to ramp. Each layer is referred to as a lift. The total height of the bank protection from toe to top is 22 feet. However, you should note that because it's a low-flow bank protection, the bulk of that height is actually in the toe, which is buried below ground. Our construction timeframe from notice to proceed to acceptance will be a little over 3 months, and the project cost is just under $2 million, which is funded exclusively by the Pima County Regional Flood Control District tax levy.
My name is Rick Solis of Solis Engineering Company. We perform construction administration services for the district on the El Rio Bank Protection Project. We also had Conformitech perform QA testing for our team. Our key role in this project was to monitor construction in conformance with the plan documents. Among the many interesting work activities that occurred on the project, the most interesting were those that generated additional thought from the whole team. Unknowns, such as a 13.8 kV duct bank owned by TEP, was found on site. This required the contractor and team to develop a plan for securing the bank and constructing underneath. Another interesting element is the potential correlation between compressive strength and ambient temperature. This project experienced low compressive breaks on samples that met density requirements and gradation. A contributing factor to why this may be occurring was that this last July was the hottest July on record.
Then, after a scraper has leveled the windrow of soil cement, compactors roll the lift to reach the required density. The crews work in section from ramp to ramp, layer after layer, until the soil cement rises out of the toe trench to reach its final elevation. Soil cement is placed at a width of between 9 to 10 feet and is then trimmed with a scraper blade to 8 feet for the areas above flow line. This removes the outer edge, which does not receive the same level of compaction, and if left untrimmed, would slough over time. Water is applied to keep the soil cement moist and slow the curing. This occurs even on the weekend so that the soil cement can reach its full strength. truck returns back to the soil cement plant for more material, and the cycle continues until final elevation is reached. The notch and low flow pipe that I previously mentioned will be cut into the soil cement once it's complete. After the soil cement is finished, the handrail and maintenance access gates are installed. On other projects along the Chuck Huckleberry Loop, asphalt pathway would be installed on top of the soil cement using a wider final lift to underlay the path.
Hello, my name is Kevin Latendry and I'm a project manager with SOMAS. SOMAS, along with our subconsultant, CMG Janage, were the design consultants for the El Rio Bank Protection Project. The goal of this project was to design a soil cement bank protection that could contain the 25-year storm event within the Santa Cruz River, but also allow larger storm events to enter the El Rio Preserve without negatively impacting the surrounding area. First in the design process, the Santa Cruz River needed to be modeled for the 25 and 100-year storm events to determine the elevation of the top of the bank protection and the toe of the bank protection to protect against scour from the 100-year storm event. CMG Janage performed the channel hydraulics modeling using HEC-RAS 2D. This modeling allowed us to evaluate the exchange of flow between the river and the preserve area, and also to evaluate water surface elevations within the preserve. The 2D model was extremely helpful considering proposed conditions would feature a low flow berm along the north side of the preserve and a notch within the bank protection, which would allow impact from lower storm events to flow into the preserve. Since the bank protection was to prevent the 25-year storm event from entering the preserve, larger storm events would flow in. To help maintain the ecosystem of the preserve, it was desired to have water within the preserve. To do this, a notch was designed in the bank protection to allow some water to enter the preserve from the small events. In order to control the water surface elevation in the preserve, a drainage pipe with a gate that could be manually operated was installed in the bank protection to drain the preserve when needed. Second in the design process, an alignment and profile for the top of bank were set. Utilizing Civil 3D and an alignment, profiles, and corridor model of the bank protection were created. From this corridor model, the proposed surface was generated and merged with the existing surface for modeling. This new surface was used for the proposed conditions in the HEC-RAS 2D modeling. Evaluation of the bank protection was a little bit of an iterative process to set the top of slope elevation. By creating a detailed Civil 3D corridor model, adjustments to top of bank protection could be quickly and easily be made to revise the proposed surface. The revised surface was then exported to RAS 2D for modeling. A few iterations were performed to achieve the final elevation. Along with evaluating the top of bank protection for the 25-year event, the toe of the bank protection was also evaluated for scour from the 100-year storm event. Again, by simply adjusting the profile elevations of the toe of slope, the corridor model could be revised. Lastly, as part of Pima County's ongoing channel maintenance for the Santa Cruz River, approximately 150,000 cubic yards of material was removed from the wash. This material was used to construct a 50-foot wide berm along the preserve side of the new bank protection, as well as used to create landscape features within the preserve.
On behalf of the ASCE Southern Arizona branch and the Pima County Regional Flood Control District, I'd like to thank you for joining us on this virtual tech tour of the El Rio Preserve Bank Protection Project. The ASCE Southern Arizona branch would also like to thank all of the people that contributed to this video, including our narrators, Solis Engineering for the drone footage, and Jose Aguilar for audiovisual editing.